Okay, so as usual, let's go over some of the things we covered last time. So last time we talked about quotients, and the goal was to think about quotients by parabolic subgroups, which are projective varieties that are quotients of G. And to get there, we needed to set some abstract stuff up about quotients. So if we have a G being a linear algebraic group and H a closed subgroup, then there's a notion of the quotient of G by H. This satisfies a universal property, and it can be constructed as a certain variety. So I gave you the outline of the construction. And in the construction, we saw that the quotient appears inside as an orbit of G acting on a certain projective space. And as a consequence, G mod H is a projective variety. And also I kind of indicated some of the ideas. I didn't prove it fully. I indicated some of the ideas of showing that if H is a normal subgroup, then the quotient is an affine variety, and it has the structure of a linear algebraic group. Okay, and then we had this notion of complete varieties. So this is an adaptation of, this is the analog of compactness in Hausdorff spaces, locally compact topological spaces. I know the terminology is a bit confusing. I sent some clarifications by email and some links, so hopefully that helps in straightening out some of this conclusion. But we just take this definition of completeness, and we use that as our kind of notion of, as our analog of compactness. And we saw that A1 is not complete, and in fact AN is not complete. Any projective variety is complete. This is not, again, this is something I didn't go over the proof of, but it's in the book. And yeah, so we had this result about complete variety. So the image of any complete variety is again complete, and so on. And the only varieties that are both affine and complete are finite varieties, dimension 0 varieties. Okay, so we had all that. I mentioned abelian varieties. So abelian varieties are connected algebraic groups that are complete as of varieties, and they're always commutative. And yeah, linear algebraic groups are kind of orthogonal to abelian varieties in the study of algebraic groups. So yeah, so then we had the definition of a parabolic subgroup. So a parabolic subgroup is a subgroup of G, a closed subgroup of G, such that the quotient G mod P is complete as a variety. Equivalently, we could have said that G mod P is projective as a variety. And we had some examples. So GO2, SL2, GO3, and then over here, GLN. So, and there was some homework about the flag variety for GLN. So hopefully you got a chance to look at that. So then, yeah, we had some more, we had some results about parabolic subgroups, kind of how they interrelate with each other. And then we had this important result that, so the definition of solvable group, and the result that a connected linear algebraic group is solvable if and only if it contains no parabolic subgroups. So somehow the existence of proper, sorry, I didn't say proper, if and only if G contains no proper parabolic subgroups. So the existence of proper parabolic subgroups hinders a group from being solvable. So, and then right away we see that GLN and SLN are not solvable because they have proper parabolic subgroups. So this was an important result, and I went through the proof. Yeah, and a corollary of this theorem is Burrow's fixed point theorem that says that any connected solvable linear algebraic group acting on a complete variety has a fixed point. So yeah, it follows pretty quickly. And then we had this definition of a Borel subgroup. So if we have a linear algebraic group G, a Borel subgroup is a maximal closed connected solvable subgroup. So yeah, so and there's this results that the Borel subgroup, any Borel subgroup is parabolic, and in fact, a closed subgroup of G is parabolic if and only if it contains a Borel subgroup. Yeah, and in fact, any two Borel subgroups are conjugate. Yeah, so that was the result about Borel subgroups. And yeah, the proof is pretty long, I guess. And then we had this corollary that I didn't go into the detail for the proof, but if we have a surjective map of linear algebraic groups, then parabolics get sent to parabolics, Borels get sent to Borels. Okay, and yeah, I mentioned this exercise, so I think that's about where we stopped last time. Any questions on this material? All right, so there's a few more things I want to say on this topic of Borel subgroups and parabolic subgroups, and then we'll move on to the main topic for today, which is reductive groups. So first of all, I mentioned this theorem before, but I wanted to isolate it and put it on its own. So the Lee-Colchin theorem is that if we have a connected solvable linear algebraic group, and we embed it inside of GLN. So this, by this subset or equals to sign, I mean closed embedding. Then we can always conjugate. This image in so that it's in the subgroup of upper triangular matrices. And this pretty much follows directly from the result that a group is solvable if and only if it has no proper parabolics. So yeah, so you think about so if G embeds inside of GLN, then it acts on the vector space K to the N, and it acts on the corresponding projective space, which is a complete variety. And so you can either go through the same argument that we saw in the proof of this theorem, or you can use the Borel fixed point theorem. Anyway, we have that, which is good. And now I want to mention a few results that I won't go over the proof of. I'll indicate some things about the proof, but I will need them. And so this result is about connected solvable linear algebraic groups. So let G be such a group. Then the commutator subgroup is closed, connected, and unipotent. It's also normal. It's always normal in any group. But in this case, it's the key word here is it's unipotent. So if we start with something that's solvable, then its commutator subgroup becomes unipotent. Also, if we think about so when we talked about the Jordan decomposition, we proved that any linear algebraic group has a set of unipotent elements and a set of semi-simple elements. And if we look at this set of unipotent elements of G, so for a general linear algebraic group, this is just some set. It's not a subgroup. But for it's always a closed subset, but it's not a subgroup. And for a solvable group, the subset of unipotent elements is it's a subgroup, and it's in fact a normal subgroup. So it's a close connected normal unipotent subgroup of G. So in particular, the commutator subgroup is contained inside of the GU. Okay, and also if we pick a maximal torus of our group G, which is solvable, then this multiplication map T cross GU to G, which this map is just given by multiplication of elements, is an isomorphism of varieties. So this should remind you of the result we saw with commutative groups. So if we had commutative groups, then we proved that the set of semi-simple elements form a subgroup, and the set of unipotent elements form another subgroup, and this product map is an isomorphism of, in that case, it was an isomorphism of groups. In this case, it's not in general an isomorphism of groups, but it's an isomorphism of varieties. So that's the result, and I'm not, the only thing I want to say about the proof is that you embed things inside of the Borel subgroup of GLN consisting of upper triangular matrices, and then you reduce it to proving these facts about Bn, and we've kind of already seen how this works for Bn, or at least it's easier to convince yourself for Bn. So and this, as I said here, this is this map is an isomorphism of varieties, but not an isomorphism of groups in general, and in many cases this will be a semi-direct product. So GU will always be normal, and GU will be the normal one, and the solvable group will be a semi-direct product of its unipotent elements by a maximal torus. That's what I said here. Okay. I think this may be true always. I think in all the examples I know this is true, the semi-direct product, but it's not proven in Springer, so that makes me think maybe there's some exceptions. Okay. So that's that result. So now let's kind of apply some of these results to a general linear algebraic group. So the previous result was only about solvable. So using the previous results, one can show that any maximal torus of any linear algebraic group lies inside a Borel subgroup. Any two maximal tori are conjugate. And also this result that actually takes quite a bit of work to prove that I'm just going to cite here. The normalizer in G of any Borel subgroup is itself. Right. So
this is normal, or it's exactly like saying that B is normal or not?
No, it's like B is as far from normal as possible. So if B were normal, then the normalizer in G of B would be G itself.
It's the opposite. Okay.
Yeah, it's like as far away from normal as can be. And as a consequence of this fact, together with the fact that any two Borel subgroups are conjugate, we have a bijection. So we can think of G mod B. So we already thought about this geometrically, at least in the case of GLN as this flag variety, but we can also think of it as parametrizing the set of Borel subgroups of G. So if we let this curly B be the set of Borel subgroups of G, then we have an action of G on this set. And the action is just by conjugation, since any conjugate of a Borel subgroup is again a Borel subgroup. And it's transitive, since any two Borel subgroups are conjugate. And it's the stabilizer of a specific Borel subgroup is the normalizer in G of that Borel subgroup. But this part 3 here, which is states that this normalizer is just B itself. So that's why this space of Borel subgroups, in fact, can be identified with G mod B, and that gives it the structure of an algebraic variety. So that's another way to think about the flag variety as the space of Borel subgroups. Okay, so that's that. I realize there's various things that I have not proven due to time constraints, but hopefully I've given you some idea of how things work with Borel subgroups and with solvable subgroups and so forth. Okay, any questions on this PDF before we move on? Okay, so next topic is reductive group. So these notes are on the website. Yeah, so, okay, yeah, let's just jump right into it. So if we have a connected linear algebraic group G, so recall, like we just talked about, a Borel subgroup is a maximal closed connected solvable subgroup. Now, new definition. The radical of G is the maximal closed connected normal subgroup of G. So the Borel subgroup is not normal. I said the, but any Borel subgroup is not normal. But the radical is the maximal normal solvable subgroup, and it's unique because you can take. I think I made a remark here. Yeah, if you have two subgroups and they're both normal and solvable, then if you take their product, so the set of all elements that can be expressed as a product of something in one group and something in the other subgroup, then that's again a normal solvable subgroup. So that's just basic group theory. So that's why the radical is the unique maximal closed normal solvable subgroup. And similarly, the unipotent radical is the maximal closed connected normal unipotent subgroup of G. So it's normal and it's unipotent. Okay, so those are the definitions. A few more definitions before we talk about examples. So we say that a linear algebraic group is semi-simple if the radical is trivial. So if it doesn't have any normal solvable subgroups. And it's reductive if the unipotent radical is trivial. So if it doesn't have any unipotent normal subgroups. It can still have other solvable or unipotent subgroups, but they're not normal if G is semi-simple or reductive, respectively. So that's what reductive means and what semi-simple means. So these definitions maybe look a bit arbitrary and unmotivated. I'll try to give a little bit of motivation about this in a few minutes when I talk about the connection to representation theory. But
Are
for
they
now,
always?
what's the question?
Okay, just are they always exist? You didn't prove they exist. You just say that they are unique.
What, semi-simple groups and reductive groups, or
No, the radical and the.
yeah. So I mean the trivial subgroup is always unipotent and solvable and normal and connected and closed. So yeah, at least you have the identity.
Oh, because you have a chain of closed subgroups.
Exactly.
Okay, this is it.
Yeah, we'll see some examples in a bit, so it should become clear. So one thing you can show pretty easily is that the unipotent radical is in fact the set of unipotent elements of the radical. So the radical is in particular a solvable subgroup, and I just cited this result that says that the unipotent elements in a solvable subgroup form a normal subgroup. So by this I mean that normal subgroup inside the radical consisting of unipotent elements, and it's pretty easy to show that that's the same as the unipotent radical. And in particular, it's contained in the radical. So if you have something that's semi-simple, then it's automatically reductive. So semi-simple implies reductive. Yeah, so we have that. So one exercise at this point to get used to these ideas, if you have a group G with a faithful finite dimensional irreducible representation, then G is reductive. So all three adjectives are important: faithful, finite dimensional, irreducible. And if you have that, then if you have such a representation, then G is reductive. So as a hint, you can use this exercise from chapter 2. So yeah, again, this week I'm gonna make my own sheet with exercises, not have exercises from the book. So this will be one of them, and I'll post it I'll email it and post it on the website soon after the class. Right, okay, so we have this, and so once you convince yourself of that, then you see automatically that GLN, SLN, and SON are reductive groups. Also, you can argue pretty easily that tori are semi-simple groups, and hence they're also reductive. The Borel subgroup of upper triangular matrices inside GLN is an example of a group that's neither semi-simple nor reductive. In fact, it's solvable. So its radical is itself, and its unipotent radical is the upper triangular, the subgroup of upper triangular unipotent matrices, upper triangular matrices with ones along the diagonal. So, so again, these notions of semi-simple and reductive are kind of orthogonal to the notions of unipotent and solvable. So if we have any connected linear algebraic group, then if we quotient by its radical, then we get something that's semi-simple. And if we quotient by its unipotent radical, then we get something that's reductive. Yeah, so we can always pass to the, I guess this is sometimes called the semi-simplification of G, or the reduced version of G. And we'll see that from the perspective of finite dimensional representation theory, it's enough just to work with the reductive version of G. So there's nothing to be gained in terms of, well, from one perspective, there's nothing to be gained by thinking about representations of the radical. I'll say more about that in a bit. Okay, so first sort of result about reductive groups. So if you have a group that's reductive, then it's radical. So reductive means the unipotent radical is trivial. So there's no unipotent radical, but there's still some radical because it might not be semi-simple. So that radical is always a central torus. And the intersection with the commutator subgroup is finite. And so the commutator, and finally the commutator subgroup is semi-simple. So how does this work? So to prove the first point, we need to recall some things that we had from before. So one is this fact that I just mentioned from the previous PDF, that if you have a connected solvable group, and you have a maximal torus, then this multiplication map is an isomorphism of varieties. And the second fact is that if you have a torus in G, not necessarily a maximal torus, then the connected component of its normalizer in G is the same as the connected component of its centralizer in G. So this is something we proved this in the chapter in the section about tori. We had this result about the rigidity of tori, and this was a corollary of that result. Okay, so how do we use these results to show the fact? So in the lemma, we have G connected reductive group, and we want to prove something about the radical. One thing to observe is that the unipotent elements in the radical is the same as the unipotent radical G, and that's trivial because G is reductive. And now we think back to this result here, and since this part is trivial, then the solvable group is in fact a torus. So Rg is a torus, the radical is a torus. It remains to show that it's central. Well, okay, so then we want to use this, so with T being the radical, and we know that it's a normal subgroup. The radical is a normal subgroup, so the normalizer is all of G. G is connected, so the connected component part doesn't matter. So that means that it's in fact, G is in fact equal to the centralizer, but then that means that the torus, the radical, the torus in question is central. So that's how that works. We've shown that any reductive group, the radical of any reductive group is a central torus. Okay, so now for the next part, we want to show that the intersection of the radical with the commutator subgroup is finite. So how do we do this? So first of all, we can, as usual, we can embed G inside of GLN. So that means that G has this faithful action on V, on this vector space V of finite dimensional vector space of some dimension. And in particular, the radical acts on this vector space V. The radical is a torus, and we had this result that the tori have pretty nice representation theory. Any representation of a torus splits up as a direct sum over the characters of the torus. So that's what's happening here, where the direct sum corresponding to the character chi is all the elements in the vector space for which the action of the torus is via this character chi. So we argued earlier that any representation of a torus splits up in this way. In fact, any representation of a diagonalized group. So we have this decomposition of V, and yeah, just a note. So this is a sum over all the characters of the torus, which is some lattice. But they'll be mostly zero. So since V is finite dimensional, only finitely many of these will be non-zero. So really, we're only concerned with that set of chi for which this V chi is non-zero. And now we use the fact that the torus is the radical is central. So that means that each of these V chi's is actually a representation of G itself. Since the radical is central. Okay, so that means that G acts on each of these V chi's. So we have an action map, R rho sub chi from G to GO V chi. We only consider the ones for which V chi is non-zero. And that means, and since G embedded inside of GLN, we see that in fact G embeds in this product of GOV chi's. So you can think of this product as embedding inside of GOV, and G factors through this product of groups. Okay, so yeah, the chi's component of this map is rho chi. Okay, so great. So what do we do now? So remember, we actually want to show something about the intersection of the commutator with the radical. So we need a little bit of setup for the next step. So for any n, I'm going to use the notation mu sub n for the nth roots of unity inside of K. maybe it's better to write K star here. But so this is just a finite subgroup of nth roots of unity. And I'm gonna, and for any chi, we have the subgroup of GL V chi consisting of scalar matrices that are where the scalar is a root of unity. And it's dim V chi root of unity. So it's an nth root of unity where n is dim V chi. So these are just scalar matrices. Okay, and so now the claim is that anything, if we have something in that's both a commutator and in the radical, then its image under one of these rho chi's belongs to this subgroup, that's this finite cyclic subgroup of GL V chi. So once we have this, then we're done, because then this intersection embeds in a product of finite groups, so it must be finite. So let's see why this works. Well, it's a little trick. It's pretty straightforward, actually. So if we have something that's both in the intersection and the radical, then first we think about it as in the radical, and let's compute the determinant of rho chi of G. Well, since we're thinking of G as something in the radical, we know that anything in the radical acts by the character chi on V chi. So in fact, so that means it acts by a scalar matrix, and that scalar matrix has determinant equal to the scalar in question to the power of the dimension of V chi. So we just compute the determinant in one way. Now let's compute this determinant in another way. We think of G as something as living in the commutator. So it's a commutator of some two elements, X and Y and G. And let's compute the determinant again. Well, now we see that this determinant has to be 1 because we just write it out as a commutator, and determinant is multiplicative. So we get cancellation and we get 1. And so that means that that means that chi of G to this power is equal to 1. And that means that chi of G is a root of unity. And so that proves the claim. Right. So, okay, so, and then this finishes up the proof, because it means that the intersection of the commutator and the radical embeds it to this product of finite cyclic groups, so it must be finite. Okay. And finally, I'm going to leave the third part of this proof as an exercise. It'll appear in the homework sheet. Okay, any questions about the first two parts of this, the proof of the first two parts of this lemma, or other questions about reductive groups so far? All right, so just to summarize, so if we have a reductive group, then we've shown that its radical is a central torus, and the commutator, so you'll show that the commutator is semi-simple, and the commutator intersect the radical is just some finite subgroup. All right, so what's an example? So you can recall that the center of GLN consists of just scalar matrices, scalar invertible matrices. It's isomorphic to the multiplicative group. So as a consequence of this theorem, we can see that, or this lemma, we can see that the radical of GLN is just the center. And why is that? Well, the center is itself, in this case, a closed connected normal solvable subgroup. So it must be contained in the radical, but then we just showed that the radical is, so we already know GLN is reductive, And so the radical must be a central torus, so it must be contained in the center. So that gives us opposite inclusion, and so we're good. So we have this corollary. And there's also a result that says, so what we just showed is that if what was part of the lemma is that if you have a radical subgroup, then its commutator is semi-simple. And in fact, it's true that if you have a semi-simple group, then it's equal to its own commutator. And so, yeah, so it kind of, you can think about, if you start with something that's radical, you can pass to the commutator subgroup. So that's semi-simple, but then if you take further commutators, you don't go anywhere. You just stay at you just recover that semi-simple group itself. So I won't prove this theorem now. I'll say, so for now, one ingredient of this proof is to prove it for SL2. And I'll leave that as a homework exercise with some broken down into some steps. So that's, and then the rest of the proof, or at least I'll give you, the rest of the proof will appear later on, or at least an indication of the rest of the proof will be given later on. But it comes down to showing that any semi-simple group is generated by subgroups that are isomorphic to SL2 or PSL2. And once you know that SO2 and PSO2 are equal to their own commutator, then you can conclude that the whole group is equal to its own commutator. So I'll say more about that later, but I wanted to mention it now because of this corollary that if G is reductive, then in fact it's the product of its radical and the commutator subgroup. So I'll ask you to prove this as part of the homework. When assuming, so you can use this theorem and then deduce that this is true. This corollary is true. Okay, so there we go. So we have that. So now I want to talk about the connection to representation theory, which kind of motivates some of these, the study of these groups. Okay, so first of all, I'm going to focus on characteristic zero representation theory and finite dimensional representation theory. So everything is, all representations will be finite dimensional over an algebraically closed field of characteristic zero. I think, I mean, the things work in a similar way in positive characteristic. You just have to be careful when some things are divisible by, like some orders of groups are divisible by P. But I think it's the representation theory is also understood over positive characteristic. But in general, in this class, we're focused on characteristic zero. Okay, so first, some more terminology. If we have a representation of a linear algebraic group, we say that that representation is semi-simple if it decomposes as a direct sum of irreducible representations. So that's maybe a more self-explanatory use of the word semi-simple. And yeah, in fact, this definition works for any group, any abstract group. Doesn't need to be linear algebraic, but we're focused on linear algebraic groups. Okay, so for example, any representation of a finite group is semi-simple. That's something you learn in a representation theory, first representation theory course. It's, or from Maschke's theorem. We saw from before that any representation of a diagonalizable group is semi-simple. So that's one of the things we proved about diagonalizable groups, in particular tori. If you want to have an example of a representation that's not semi-simple, the go-to example is the following. So you take the additive group GA and you embed it inside of GO2 in this way. So lambda goes to the upper triangular unipotent matrix with lambda on the top right. And this is not semi-simple, so it's not irreducible. The span of the first basis vector is a sub-representation, but there's no complement. You can't decompose it as a direct sum. Okay, so we have that. So that's some terminology. And now, the connection to the semi-simple linear algebraic groups. So if our linear algebraic group happened to be semi-simple, then in fact every finite dimensional representation of G is semi-simple. So it breaks up into irreducible components, as it breaks up into a direct sum of irreducibles. So again, I don't think I'll go through a full proof of this theorem. I do want to give you a key construction that makes everything work. So let me point out that, because it also highlights some nice ideas. So if you have, let's suppose G is a semi-simple linear algebraic group. Let's take V a representation of G. Then, as we discussed, we get a corresponding Lie algebra representation. So the Lie algebra of G, this is the Lie algebra of G, maps to G of V. So this is this Lie algebra of endomorphisms of V, and this is a map of Lie algebras. So it's a representation of the Lie algebra. And now, equipped with this representation, we define a symmetric bilinear form on the Lie algebra. And we do this as follows. So we take Lie algebra tensor Lie algebras to the ground field K. And the way we define this is by taking two elements xi and xi prime in the Lie algebra and sending them to the trace of the product of the corresponding endomorphisms. So an xi and xi prime define endomorphisms of V. So we use rho to map them into G of V. We take the product of those two endomorphisms. So this is just composition, and then we take the trace of that composition. So this is a symmetric bilinear form. So it's pretty so it's bilinear in each factor, and it's symmetric because the trace is symmetric. The trace of a product is the trace of the product in the opposite order. So now you need to argue that if G is semi-simple, so radical is trivial, then that implies that the kernel of this pairing is trivial. So that I won't do, because it requires a little bit of Lie algebra theory. So there's the notion of a solvable ideal in a Lie algebra. And if the radical of a group is trivial, then there are no non-trivial solvable ideals in its Lie algebra. And the kernel, and then on the other hand, one shows that the kernel of this bilinear form is always a solvable ideal. So therefore it must be trivial. So yeah, so that's the sketch of that part. Okay, so since the kernel is trivial, this symmetric bilinear form, that means is a non-degenerate form. And what that means is we can find bases of two different bases, potentially different bases of the Lie algebra, such that if we take, so they're both indexed by the same set, so E1 through En, if n is the dimension of Lie algebra, E1 through En prime, so E1 prime to En prime. And these bases have the property that Ei paired with Ej prime is equal to 1 if I and j are the same and 0 otherwise. So that's, yeah, this is just some general stuff about symmetric bilinear forms that are non-degenerate. And if we have, so once we have these two bases, then we get this, we get this operator on V. So we take these two bases and we form the following operator inside endomorphisms of V. So we take rho I composed with rho E sub I composed with rho E sub I prime and the product over all i's. And this lives inside of GLV, but in fact, you can show that this is this commutes with the Lie algebra action. So that's, again, something else that I won't go into, but you show that this commutes with the Lie algebra action. So it defines the Lie algebra, so G being the Lie algebra, frac G linear endomorphism of the vector space V. Okay, and so then because this is linear for the Lie algebra, its kernel and its co-kernel will again be representations of G, and using that, if you have a sub-representation, you can construct a complement. So I'm not going to go through the details there, but I guess yeah, those are the important tools. Those are the things I wanted to highlight here. So you can think. So I like Milne's chapters on representation theory of linear algebraic groups and the various notions and how they're related. So you can, if you're curious about a full proof, you can read chapter 22 of Milne. I think it also references some things in chapter 21. So maybe you need to read a bit more, but it's explained in there. So some notes on the terminology. These things that appear in the proof are actually quite prominent and appear in lots of other places in representation theory. So this operator CV on V is called a Casimir operator. And in fact, these Casimir operators can be used to, they're related to the center of the universal enveloping algebra, so you can use them to understand the center of the universal enveloping algebra. But they appear a lot in representation theory. And also, so going back to the pairing, if we took V to be the adjoint representation, then we get a pairing on the Lie algebra, symmetric bilinear pairing on the Lie algebra, and that's called the Killing form. So maybe that's something else that you'll encounter. Okay, so that was a sketch of some of the ideas that go into this proof. So again, the upshot is that the finite dimensional representation theory of any semi-simple linear algebraic group is semi-simple. So any finite dimensional representation of a semi-simple linear algebraic group breaks up into a direct sum of irreducibles. Okay. And just one more thing. If you want to think about a specific example of this construction, so if you think about SL2 and adjoint representation, then you can write out what the Killing form is. So the Killing form would just be the trace of the product of two matrices, and the Casimir operator would be this operator. So we take adjoint E. So the two bases would be E, F, and I guess 1/4 of H, and then F, E, and 1/4 of H, and this would be the corresponding Casimir operator, if you're curious. But this stuff about Casimir operators and Killing forms, it's in the side, so don't worry about it too much. Okay, I think this is a good time to take a break. So let's take a 5-minute break, and and see you in 5 minutes. Okay, so we saw that, and just one follow-up note on that. So if we think back to, so you may ask, what's the advantage of thinking about the Lie algebras, the Lie algebra of a linear algebraic group? We saw that in this proof, we had this bilinear form on Lie algebra. So we were able to do some linear algebra on it, on the Lie algebra, because the Lie algebra is a vector space. And that's not something that we can do on a group. We can't do these sorts of bilinear operations or whatever on the group. So this is one point where you see the advantage of working on the Lie algebra side of things. Of course, there's some translation that needs to be done. That normal solvable subgroups become solvable ideals and so forth. Okay, so we had this result about semi-simple groups. So now we have the following corollary. If we have a connected reductive group, okay, this is not stated well. If we have a connected linear algebraic group, let me fix this right away. If we have a connected linear algebraic group, then the following are equivalent. G is reductive. Any finite dimensional representation of G is semi-simple, and G has faithful finite dimensional, has at least one faithful finite dimensional semi-simple representation. So this means that, so we saw that reductive groups have this property that their finite dimensional representation split up, but they're not the only groups that have this property. So reductive groups also have the property that any finite dimensional representation splits up. And in fact, they're exactly those groups that have this property. Any group that has a representation that does not split up into irreducibles, as does not split up as a direct sum of irreducibles, cannot be reductive. Okay, and in fact, part C says that it's enough just to find a single faithful finite dimensional representation that's semi-simple. All right, so let me give you the idea of the proof. So we're going to use this theorem that I just outlined about semi-simple groups. So if G is reductive, then we know that the radical is a central torus. That's what we showed earlier today. And so once we have a representation of G, we can decompose it in terms of characters for that central torus, for the radical. So that's what we did previously in a different proof. And again, only finitely many of these v chi's will be non-zero. And each of these v chi's, so since the radical is central, each of these v chi's will be a representation of v itself. And in particular, it's a representation of the commutator, since the commutator is a subgroup of G. So any representation of G is also a representation of the commutator. And I said previously, and this is something you think about in the homework, that this commutator is a semi-simple algebraic group. So therefore, each of these v chi's as a representation of the semi-simple algebraic group splits up into irreducibles. So that means, so each v chi decomposes the direct sum of irreducible representations of the commutator. So that means, for each v chi, we have some index I and some subspaces of v chi that are irreducible representations of the commutator. Okay, and finally, we use the fact that the group is the product of the commutator and the central torus, which is the radical. And so that implies that each of these v chi's is in fact an irreducible representation of G. And because we already know it's an irreducible representation of the commutator, we already know that that the radical just acts by a character chi on it. So using those facts, it's easy to deduce that in fact it's an irreducible representation of G. Actually, maybe it won't be irreducible, but it'll be a direct sum of copies of the same irreducible representation. So it'll be just yeah, well, it defines a single irreducible representation in G, but maybe multiple copies of it. Okay, so that implies B. So that implies that any finite dimensional representation of a reductive group is semi-simple. So yeah, so we see that reductive groups are kind of built out of this semi-simple piece, which is the commutator, together with the central torus, and each of those has this nice property that their representation split up, and so playing these two things off of each other, we get that the whole group has this property. Okay, and now the fact that, okay, so to prove B implies C, that's immediate from the embedding theorem. So B says that any finite dimensional irreducible representation is semi-simple. And C says that there exists a faithful finite dimensional semi-simple representation. And if we think about, if we embed G inside of GLV, then V will be a finite dimensional, faithful finite dimensional representation. And because we are assuming B, it must be semi-simple. So there we go. And then C implies A follows from that exercise on page 2 that if you have a finite dimensional irreducible representation, then then the group must be reductive. Okay, so there we go. So this theorem, let me scroll back to the statement of the theorem, of the corollary. So this theorem gives us a characterization of reductive groups in terms of their representations. And I think, I'm not sure, but I think the name reductive comes from the fact that you can reduce things to the semi-simple case. So there's only that torus of difference, central torus of difference between reductive and semi-simple, and you can reduce the study to the study of semi-simple, semi-simple groups. I think that's where the name comes from, but I'm not sure. So, okay, so the next thing, so the big result with reductive groups is the following classification theorem. And this, this is the first pass for this classification theorem. I want to make you aware of it, and probably in the lecture next week, I'll say more about it, but I wanted to give you a preview of it so that it doesn't look as motivation. So some of the constructions don't look too unmotivated. So, okay, the classification theorem says that we can classify reductive groups in terms of certain combinatorics. So what happens is to any reductive group, we can associate a root datum, and this will be stuff in terms of root systems. I'll say more about it, but it's kind of discrete and combinatorial in nature as opposed to geometric. And we can assign this combinatorial data to each reductive group, and it characterizes it. So this combinatorial data will be an isomorphism invariant, and two reductive groups will be isomorphic if and only if their root data are isomorphic. So that's kind of the setup. So I need to say a lot more things about how this works. But for reductive group G, its root datum will be a triple X R X check art check, where X will actually turn out just to be the character group of a maximal torus. So this will be a lattice. And X hat will be the dual group, so group homomorphisms from X to Z. And yeah, so those two things are clear. Now the things that are less clear are what R and R check are. So these are root systems inside of the real vector spaces corresponding to X and X check. So yeah, so that's kind of the idea. And yeah, so that's it for this PDF. In the next PDF, I'll talk about root systems. Are there any questions so far for this, for the material in this PDF? Okay, so then let's move on to the next. The next topic, which is root systems. So yeah, I don't know how familiar you guys are with root systems. I imagine some of you have seen this before. So I've tried to kind of summarize some of the things. So if you've seen this before, then it should be, it'll be a reminder, refresher. If you haven't, then I think I'll still include enough detail that you kind of can get a sense of what's going on. And if you're interested, fill in the details. I don't imagine I'll assign too many exercises about root systems, so you can mostly just enjoy this without worrying too much. So okay, so okay, so in this game, we have V, a vector space over R. So R is a, yeah, so we're not working over an algebraically closed field, we're just working over the real numbers. And we want to equip V with a symmetric bilinear form that's positive definite. So that's just a map from V cross V to the real numbers that's bilinear. So it's really a map from V tensor V. So this is bilinearity here, and it's symmetric. So it sends V comma W to the same thing as W comma V. And positive definite means that if you have a non-zero vector, then it's the pairing with itself is always a positive number. Yeah, positive semi-definite means this could be equal to 0, but it's positive definite, so it's bigger than 0. So symmetric bilinear, that's what a symmetric bilinear form is. If you haven't seen symmetric bilinear forms before, you can just think of this as the dot product. So it's a fact that if we have a positive definite symmetric bilinear form, then there's a basis of the vector space V, in which this pairing becomes just the dot product. So the usual dot product, so the sum of the products of the corresponding entries. So X is a vector x1 through xn, Y is a vector y1 to yn. We have the usual dot product. And that satisfies all these properties. So you can, in fact, in the examples, this pairing will always be the dot product, but it's good to set things up a bit more generally. So we have that. Okay, and so the next thing is the notion of a reflection. So if we have a non-zero vector in our vector space, the reflection, so it defines a reflection of the vector space, and this is it's a linear map that sends V to its negative and fixes the hyperplane of elements orthogonal to V. So that's what you want a reflection to do. Like you have some plane and you're reflecting across this plane, and V, or vector V, will be sent to its negative, and the plane will be the set of all vectors orthogonal to V. And if you think about what it should be in terms of a formula and in terms of this pairing, which this pairing is what allows you to say that something is orthogonal to something else. So the orthogonal complement of V is all the W's for which this pairing vanishes. Okay, so this is the formula. So W goes to W minus 2 times the ratio of the let's just say dot product of V and W with the dot product of V in itself, and this is multiplied times V. So we take W minus some multiple of V. Yeah, and this is, yeah, okay. So if we have a quick example, if we have V with V being R2 with the dot product, and we take little v to be this vector 2, 1, then you can calculate what this SV is doing. And as a matrix, it's this matrix. And it fixes the orthogonal complement of V, which I guess would be the span of -1, 2. And so, yeah, that's the orthogonal complement, and it fixes that. So, yeah, so that's that. Yeah, any reflection is really some higher dimensional picture of this. Okay, so if we have a reflection, some things to note. First of all, it takes any multiple of V to its negative. So if we think about just the one-dimensional subspace spanned by V, on that it acts like as a flip, multiplication by -1. Also, because we define it in terms of the vector, that the reflection across the vector is the same as the reflection across any multiple of the vector. So S lambda times V is equal to SV for all real numbers lambda. And the fixed points of a reflection, of the reflection across V, are exactly those W for which V pairs with W to 0. So in other words, the orthogonal complement of V. All right, and if we do a reflection twice, then we get the identity. So all these things, yeah, so there's one more thing, and this is, this reflections respect the pairing. So, so if we take two vectors and we reflect them, and then compute the pairing, this bilinear form, then that's the same as first. That's the same as first as what we would have gotten if we just computed the pairing to start with. So all these things you can just check from the formulas, but I think they confirm that this is the right definition of a reflection, because we want a reflection to satisfy all these properties.
You said that we're walking over R, so it's must be an inner product, right?
Yeah.
Okay.
Yeah, exactly. Yeah. Non-degenerate inner product. Okay, so there we go. Okay, so that's the definition of a reflection. Now we have the definition of a root system. So we have our vector space V with this inner product, symmetric bilinear form, whatever you want to call it, just dot product basically. And a root system inside of V is a finite set of non-zero vectors that I'll denote by capital Phi. And this set satisfies the following conditions. So first of all, the roots span V. So if we take V, so if we take phi and okay, I'll have some more clarifications. Let me just read out the axioms and then I'll clarify what they mean. So first the root span V. Second, anytime we have a vector in phi, so a root, then the only other multiple of that vector alpha that's in phi is negative alpha. So for any root, it's negative is in phi, but no other multiple would be in phi. And the third thing is that if we take any root and we consider reflection across that root, so we form the hyperplane orthogonal to that root and we reflect, then that sends phi to itself. And finally, if we have any two roots, then if we compute this quantity, so this is the inner product of alpha and beta divided by the inner product of alpha with itself, then that's a half integer. So it's either an integer or 1/2 of an integer. I guess everything that's 1/2 of it. Yeah, integers are also 1/2 of integers, so it's a half integer. So some clarifications about this. So first of all, the first condition, first axiom means that if you take this finite set of vectors and you could consider it span, then you get all of V. Second means that, yeah, I guess I already said it, that if alpha is in phi, then negative alpha is also in phi, but no other multiple of alpha is in phi. And yeah, the third means that whenever we reflect, we send phi to itself. So it won't be fixed point-wise, but each root will be sent to some other root when we reflect. So in particular, alpha, when we reflect across alpha, alpha will be sent to minus alpha, but then the other roots will be sent to different places. We'll see some examples soon enough. And the fourth condition, which maybe is the most mysterious, it's just saying that if we project, if we have two roots alpha and beta, if when you project beta onto the span of alpha, then we get a half integer multiple of alpha. And since this condition is for any two roots, it means the same thing is true for the projection of alpha onto the span of beta. So yeah, so using the inner product, we have a notion of projection, and the various projections of the roots onto other roots are constrained by this condition 4. So yeah, we'll see this in examples. Before going to examples, I just want to state one more definition, which is the corresponding reflection group, the reflection group associated to a root system. So anytime we have a root system, we have all these roots. We have the reflections across any root, and the subgroup generated by all these reflections inside of the general linear group of V. In fact, there will be orthogonal transformations. So it's in fact inside the orthogonal group of V, but it doesn't matter. So that subgroup is a reflection group because it's generated by reflections, and it's a reflection group associated to the root system. It's also called the Weil group. We'll see how this is related to the Weil group associated to a linear algebraic group, probably in the next lecture. But anyway, we have this finite reflection group. It will turn out to be finite. Okay, so let's jump into some examples. So first example, which is the easiest thing, is where V is one-dimensional, and the root system that we pick consists of alpha, and there's only one non-trivial root system up to isomorphism, up to scaling, and for reasons that are probably mysterious for now, but will become a bit clearer later, I want to choose the root system consisting of 2 and minus 2. So those are my two roots. They satisfy all the axioms. Reflection across alpha is the same as reflection across minus alpha, and that permutes these two roots. And yeah, and all the other axioms hold. If we project alpha onto the span of minus alpha, then we get alpha itself, which is minus alpha, so minus alpha, so the fourth axiom works. So there's only one reflection, it's minus the identity, so the Weil group is just a cyclic group of order 2. Okay, so that's this pretty easy example. The first interesting example is the A2 root system. So here we have V being R2 with the usual dot product, and the A2 root system. In fact, I built it with Zoom tools. So the A2 root system has 6 roots: alpha, beta, alpha plus beta. I guess I'm doing it from my orientation. From your orientation, probably it's alpha, beta, alpha plus beta. This is minus alpha, minus beta, minus alpha, minus beta. And you can, so I've chosen So you can rescale to whatever coordinates you like, but I've chosen alpha to be the vector 2, 0, and beta to be the vector minus 1 square root of 3. And so we can see that it's a root system. So the reflection across alpha is just this flip. So it sends the root system to itself. Reflection across beta, so I guess this is beta for you, would be this. So it sends a root system to itself. And if you think about what the reflection group is, it's just S3. So you can, there's multiple ways of thinking about this, but in the end, this S alpha corresponds to this from 2 cycle 1, 2, S beta corresponds to the 2 cycle 2, 3, and you can, for example, check that the S3 relations are satisfied. And there's various ways to see it. Okay, so that's the A2 root system. And also the inner, so if you think about the projection, so this, okay, so let's see. This is alpha, this is beta. The projection of beta onto the span of alpha would fall here, and that's minus 1/2 alpha. So that's a half integer multiple of alpha. So that's fine. And if you project alpha onto the span of beta, you get minus 1/2 beta. So again, that's a half integer. Okay, so that's A2. Next we have B2. So for here, I can build it with Zoom tools because I need this green Zoom tool, which I don't have. But anyway, I drew it out here. So for the B2 root system, you have 8 roots. You have alpha, beta, alpha plus beta, 2 alpha plus beta. So you can, again, this is just a choice. You can have alpha be 2, 0, beta to be minus 2, 2. And then the reflection group will be D4, dihedral group of order 8. So the symmetries of a square, and you see the square here. So it's the unit square, and the reflections. So any diagonal reflection and a reflection across an equator or whatever those other lines are called generate all of D4. So there we go. That's one way to see the isomorphism. Okay, so that's, and here, if we project beta onto the span of alpha, we just get minus alpha. And if we project alpha onto the span of beta, we get minus 1/2 beta. So here, that multiple that we get depends on whether we, the alpha and beta have different lengths. And so when we project, we get different multiples. Okay, and finally we have, or not finally, but next we have the G2 root system, which I also have here. So in this root system, we have how many roots? 1, 2, 3, 4, 5, 6, 12 roots. And you can, so we have alpha and beta. Oh, sorry, alpha and beta. So beta, I by convention, I guess I wanted beta to be the long one. So again, we can think about what happens with reflections and so forth, and everything is preserved. The vowel group in this case is D6, symmetries of a regular hexagon. And again, we can see the hexagon here. If we think about all these the long roots forming the vertices of the regular hexagon, and then we have the reflections, so the diagonal reflections and the reflections across that connect one side to the midpoint of one side to the midpoint of the other side. Those generate all of D4, and you can also check the projections. So that's the G2 root system. And also, this is kind of simpler than the some of the previous ones, the A1 cross A1 root system. So if we have just, if we take two copies of the A1 root system and put them orthogonally to each other, then then they're kind of, then we get this, and the vowel group is Z2 cross Z2. So there'll be, well, in a minute, I'll say what the notion of irreducibility is. So the examples of A2, B2, and G2, they cover the isomorphism classes of irreducible two-dimensional root systems. This A1 cross A1 is, again, a two-dimensional root system, but it's not irreducible. You can reduce it into A1 and A1. So I'll say more about irreducibility in a second. I just want to give one final example, which is the AN root system. So this this generalizes the A1 and A2 root systems to higher dimensions. And the most canonical way to define it is as follows. So if you start with you start with one dimension higher, so Rn plus one. And then inside of Rn plus one, you pick a certain hyperplane, so an n-dimensional subspace. And this would be the n-dimensional subspace where all the coordinates add up to 0. So you pick your standard basis of Rn plus one, and you think about all the points inside of Rn plus one, where the coordinates sum up to 0. So that's just a copy of Rn living inside of Rn plus 1. So inside of V, we want to choose the following vectors. So EI minus EJ. So that's a difference of basis vectors in Rn plus 1. And the sum of the coefficients is 0, so that lives inside of V. And yeah, we take all these possible differences except for when I and j are equal, and then we get 0, so we take out 0. And we think of this as a subset of V. And it's not too hard to check that this is actually a root system. So it's easy to see that they span. You just do direct computation to see that the reflections preserve this subset, and that you get half integer multiples when you project. And what else did we need for a root system? We need, I guess that's all we need. And also it's negative. Yeah, that's the other thing. So EI minus EJ will have its negative in there because that will appear when we take, that'll appear there. We just flipped indices. And then it's also true that the reflection group is the permutation group Sn plus 1. And to see this, you have this, you have a basis for V given by EI minus EI plus 1, where I goes from 1 to n. And so those generate the vowel group, the reflection group for this root system. And you argue that that corresponds to the 2 cycle I plus 1. And so that gives you the isomorphism. So you can check that the relations are satisfied. Okay, so that's the AN root system. I don't have the green zone tools, otherwise I could have constructed the A3 root system, but this is a picture of it from Wikipedia for the picture of the A3 root system. So it lives in R3, and and you can think about what happens under the various reflections and projections. All right, so I alluded to this definition earlier, but let me state it formally. So a root system phi is irreducible if it cannot be written as a disjoint union of two root systems phi 1 and phi 2, such that they're orthogonal. So anything in any alpha in phi 1 pairs to 0 with any beta in phi 2. And technically, phi lives in some subspace vi of v, and v can be written as the orthogonal direct sum of v1 and v2. Okay. So in terms of studying root systems and their classification, one important step is to this notion of positive roots and simple roots. So a subset of a root system forms a set of positive roots if for each root exactly one of alpha and minus alpha belongs to this set of positive roots. And for any two distinct roots inside the set of positive roots, if their sum also is a root, then it must be a positive root. So this definition is a bit confusing. Let me just finish with the simple roots, and then I'll give an example. So if you have a set of positive roots, then a positive root is a simple root if it can't be written as a sum of two other positive roots. Okay, so okay. So I have this remark that choosing a positive, so let's think about the A2 root system. Choosing a positive subset of positive roots is equivalent to choosing a generic hyperplane. So if we choose a generic hyperplane, generic meaning it doesn't intersect any of the roots, it doesn't contain any of the roots, it will be something like this, for example. So that separates roots on one side of the hyperplane and roots on the other side of the hyperplane. And if we just pick one side, if we say pick this side, then these form a subset of positive roots. We could have picked these also form a subset of positive roots. If we picked one of them, then let's say we pick this side, then these two will be the simple roots. This is not simple because it's the sum of these two. If we pick this side, these two will be simple. This is not simple. But the choice of hyperplane is arbitrary. We could have chosen this hyperplane, and then this would be a set of positive roots with these two being simple, and correspondingly, these would be a set of positive roots with these two simple. We could have chosen some other hyperplane. So that's the content of this remark. And in terms of the A2 root system, it's kind of conventional to choose the hyperplane to go like this. So then alpha and beta are the simple roots. But there's really this is a convention in terms of that's not kind of too canonical. You could have chosen, I guess I give another example, you could have chosen this vertical hyperplane, and then minus beta and alpha plus beta would be the simple roots on this side. And on this side, you'd have beta and minus alpha minus beta. Okay, so that's kind of the notion of a subset of positive roots and the simple roots of that subset of positive roots.
How do you define equivalence between root system?
I'm getting there.
Okay.
Yeah, I'm getting there. Yeah, that's a very good question, and I probably should have done it earlier, but I'll be there in just a second. I know I'm running low on time. So one lemma here. So I mentioned that this constraint about the projection of a root onto the span of another root being a half integer multiple of the root you're projecting onto, that's a pretty stringent condition. It's pretty constraining. And if you work out the sort of the elementary geometry and angles and stuff, then the angle between any two roots must be a multiple of pi over 6 or pi over 4. And by multiple, I mean integer multiple. And if you've chosen some subset of positive roots, the simple roots in that subset will have angle between them always one of the following four choices. So either they're orthogonal, or pi over 2, yeah, they're orthogonal, or they're 2 pi over 3. So that's the case with the A2 root system. This angle I guess for you guys, it's this way. This angle here is 2 pi over 3. Right? Yeah, 2 pi over 3. Or it could be 3 pi over 4. So that's what happens in the B2 root system where we had this kind of square looking thing. Or 5 pi over 6. That's what happens in the G2 root system. So we had alpha and beta, and this angle over here is 5 pi over 6. And those are the only possibilities. So if you want to convince yourself of this, it's pretty easy. You just, so this angle theta satisfies the cosine of theta is the inner product of alpha and beta over their norms. And you also have this condition that these quantities are half integers. So if you multiply them by 2, they have to be integers. And so if you work things out, then that means that 2 cosine theta must be in this set. And yeah, so maybe I won't say anything more, but it's some elementary computations that let you deduce those results. Okay, so maybe, I know I'm running low on time. Let me just, what is the definition? I wanted to give the definition of, oh yeah, so I'll come back to the classification. I just wanted to end with this definition of an irreducible root, of an isomorphism between irreducible root systems. So at first I wrote just any root system, but this only works for irreducible ones. So if you have 2 irreducible root systems, then an isomorphism is an invertible linear map between the vector spaces, so the vector spaces that contain phi and phi prime. It's an invertible linear map such that it respects the norm up to the inner product up to a scalar. So the pairing. So if we take 2 vectors v and w in V, we can map them to V prime and then use the inner product on V prime and to compare these two. And that'll be a multiple of, positive multiple of the pairing of V and W in the original vector space V. So that's one condition. And the other condition is that phi gets sent to phi prime. So this is for irreducible root systems. For a general root system, you decompose it into irreducibles, and an isomorphism must be an isomorphism between each of the irreducible components, because you can do different things for the different irreducible components, like different scalars lambda. Yeah, so I think I'm out of time. If there are any pressing questions, I can answer them. Otherwise, yeah, you're free to go. Oops, I meant to stop the recording.